Hello, everyone. I'll present the POP-HGS. Our team is composed by me and Ruslan Sadikov. So I'll talk about some notation. We will consider CVRP over a complete undirected graph G, where V is the set of vertices, E is the set of edges, 0 is the depot, V plus is the set of customers. We have a cost Cij for each edge Ij, and Di is the demand for the customer I, and we have the vehicle capacity Q. The problem definition, I suppose everybody here knows, I hope so. Before describing our approach, I have to talk about two known techniques. The first one is pop music. Pop music comes from partial optimization meta-heuristic under special intensification conditions. It is a decomposition-based framework by Tayar and Voss in 2002. And its basic idea is to re-optimize parts of solutions until a local optimal is reached. It is, as this figure illustrates that, it is suitable for problems whose solutions have independent parts. So you can use some of these parts, as this blue one, as a seed to build a subproblem. In this illustration, you have this red subproblem. So you can re-optimize that part independently of the other parts. And if you manage to find a better sub-solution, you can replace and get improved the global solution. It is also similar to large neighborhood search, and it's known as ruin and recreate tool in the literature. So in Queiroga, Sadikov, and Ushoa 2021, was proposed a pop music approach for the CVRP, where the subproblems were solved via branch cut and price based heuristic. It was named BCPH, and in this work, the subproblem is a set of customers associated to a subset of the routes. The subsolver BCPH was implemented via VRP solver framework. And this approach was good in medium and long runs when compared to some state-of-the-art methods. But I would say that it's a very interesting strategy to reach improved solutions starting from the best known solutions, BKS, in long runs. It was showed in an experiment of 2020, where starting from the BKS at that time, we managed to improve the several solutions of the CVRP. Some of them are still the best ones in CVRP lib. The other technique I have to talk, it's the hybrid genetic search. These first bullet points are very similar to the previous presentation of Martin. So hybrid genetic search is a population-based evolutionary search by Vidal et al. 2012. It was proposed for many VRP variants, including the CVRP, and it has local search and an advanced control of population diversity. More recently, Thibaut Vidal introduced a new neighborhood called SwapStar to boost the performance of HGS for the CVRP. It was named HGS CVRP, and it is an open source project. So basically, our algorithm, our solver in this competition is POP-HGS, and it is almost the same as in Queiroga et al. 2021, but using HGS CVRP instead of BCPH as subsolver. This is not the first time HGS is explored as a subsolver. Very recently, we have two works, Santini et al. 2021 and Lee et al. 2021. They did some decomposition-based algorithm using HGS as a subsolver too. So now I'll describe our solver. We have the data, CVRP data, and some input parameters. Tmax is the time limit defined by the competition rules. We have also TPOP, which defines the starting point to start to solve sub-problems. It was, for the competition, we use half of the time. We have alpha and delta to control the target dimension. Target dimension is an upper bound on the number of customers for sub-problems. The method explores smaller sub-problems before the larger sub-problems. So the output is the best solution found S. DIMSP is the target dimension, which is initialized with alpha. We have a structure P to store the already explored sub-problems to avoid repetition. So the initial solution is produced by the hybrid genetic search over TPOP seconds. And then we have an iterative part, which is executed until the time limit is reached, or the sub-problem size reach the maximum size, which is the number of customers. So at first we shuffle the list of customer to define the list of seeds. In this method, customer is a seed used to build a sub-problem. So we sweep all these seeds, and for each iteration, we use the customer I to build the sub-problem VSP, which is initially empty. In this block, we iterate to pick the closest route to the seed, which is the route having the closest customer J to the seed I, and this selected route hat R is all the customers of this route is included into the sub-problem VSP in line H, only if the target dimension is respected. So when the target dimension is violated, the sub-problem is done, and we can go to the line 12 to test if this sub-problem is a new one and is not a subset of a previous sub-problem. If the sub-problem is it's good to explore, then we solve the sub-problem and update the solution if necessary in line 13. This line 13 is in fact a block of instructions where we get the current sub-solution associated with the sub-problem VSP. We store this the current sub-problem in the set of already explored sub-problem, and we define the time limit for the HGS according to table 1. These values were taken from the paper in Queiroga et al. 2021, when we define the time limit as the round and median time of the BCPH subsolver. That is, we gave the same time of BCP to HGS to trying to solve the sub-problem. And then we get the solution S prime SP from HGS, the new candidate for sub-solution. If this new sub-solution is better than the current one, we update the structure P, and we update obviously the global solution with the improved part, then improving the global solution. After that, we go to the line 2. Let me go back. So if we manage to improve the solution, we can shuffle again the list of seeds and try new sub-problems with the same target dimension. If after trying all the seeds for the current target dimension, no improvement was found, then we can in line 14 increase the target dimension and explore larger sub-problems. So here we have a figure to illustrate the process. The black customer is the seed, and we create this problem with these 4 routes, and after we optimize that sub-problem associated to these customers, we can improve the global solution, replacing the old routes with the new ones. So we did some pre-competition experiments, and it showed POP-HGS was better than the pure HGS CVIP according to the competition rules to give points for each instance. And if you consider all the instance POP-HGS have 97 wins against 44. If you consider the X instance, POP-HGS have 70 wins against 30 wins of HS CVRP. In golden instance, POP have 8 wins against 4. In the explicit instance, we have a tie, but both methods managed to find the same solution in a similar time. So we have a tie here. For the very large instance, we had to modify a bit the HS CVRP because memory issues. So the pre-computed matrix it's not a good idea, because depending on your memory, the operating system can kill your method. So we did just-in-time computing of CE for each edge. It's not so good for performance. It deteriorates the performance. But in this set, POP-HGS got 8 wins against 2, and for the other 7 instances, there is a advantage for the POP-HGS with 5 wins against 2 wins for pure HGS. In the first phase of the competition, our solver came in 3rd place with 814 points. So for the future, this solver could be improved using some classifier to select different subsolvers, for example, HGS and the BCPH, over the subproblems or even the sub-solution features. And we can try different strategies to build subproblems as the ones studied in Santini et al. 2021. Here we have the reference for these presentations. If you have some questions, feel free to do it, or you can contact us by email. And that's it. Thank you.